associate with a square matrix a number. I will denote the determinant of a matrix as, well, following the determinant of A, or maybe the determinant of the matrix A, B, C, D, or using this notation where instead of having like a parentheses or a bracket, I'll have these straight lines of the matrix A, B, C, D. I'll usually use this notation more often than any other notation. But I could use this also, depending on the situation. So let's look at some special cases for finding determinants. Suppose I want to find the determinant of the 2 by 2 matrix, A, B, C, D. Then it's equal to A times D minus B times C. In the 3 by 3 case, the determinant of the matrix A, B, C, D, E, F, G, H, I is A, I, E plus B, F, G plus C, D, H minus G, E, H, F, A minus I, D, B. So how to remember these special formulas for the 2 by 2 and the 3 by 3 case. So one way of remembering it is to use the following. I multiply this way, AD. And when I do that in this direction, I'll put a plus sign in front of this. Then multiply in this direction. When I do that, I'll put a minus in front. And so it's just AD minus BC. Or remember this. So if I go in this positive direction, I would do the first element times the second in the first row times the second in the second one. Go in the other direction, so they'll be opposite the arrow, so you have to do a minus. It's minus the first. So it's AD minus BC. Another way, so for 3 by 3 matrices, I would write out the first 2 columns, then multiply in this fashion. I put a plus. When I multiply in the other one, I'll subtract. So you add going this way, subtract going that way, where you've added the first 2 columns, where you have placed these first 2 columns in those locations. Next, I could use this to remember 1, 2, 3. So I do go 1, 2, 3. So first, second, third. So first times second times third, that's a plus. 2, 3, 1. So 2, 3, 1. That so B, so A, E, I plus B, F, G plus. So that's 1, 3, 1, 2. So 3, 1, 2 plus C, D, H. Go in the other direction. Say 1, 3, 2. 1, 3, 2 minus A, F, 1, 3, 2. A, F, H. Minus 3, 2, 1. Minus 3, C, E, H. C, E, G. C, E, G. I pointed, but I said the wrong thing. And so you would just if you go in this direction, it's plus because you're going the right direction, and it's minus because you're going in this other direction. And you would hit all three going this way and all three going the other way. Okay, actually, it said 5 of, okay. So note that these tricks do not work for 4x4. So these two tricks that I've shown you in these cases do not correspond to tricks in higher dimensions. This one actually does, but okay, so because of that, we will be using minors and cofactors. For one thing, the higher order tricks, the higher order ones, become just too computationally intensive, and it's much easier to do these other ones. It won't be nearly as computationally intensive. Suppose you have a matrix with whose ith jth entry is a sub ij. Then the minor of a sub ij for the matrix, whose ith jth entry is a sub ij, which is an m by n matrix. This minor will be denoted by m sub ij, and it'll be equal to the determinant of the m minus 1 by, these are both n's, even though I said it. So the n minus 1 by n minus 1 matrix formed by deleting the ith row and the jth column, the original matrix. The cofactor of a sub ij is denoted by c sub ij and is equal to -1 to the exponent I plus j times this minor, m sub ij. The determinant of the matrix A is just the sum, I equaling 1 to n, -1 to the I plus j, A sub ij times m sub ij. And so it's the sum of minors, which is equal to, if you want to do it the other way, the sum, so of expanding along, the sum j equal 1 to n, -1 to the I plus j, a sub ij, m sub ij. Theorem. If every entry in a row or in a column of a determinant is 0. So that's an easy way to see that determinants are 0. We'll also see some other ways, but the effect of a row or column operation on the value of a determinant. Let A be the original matrix, let B be the matrix after the row operation, or column operations if we're talking about them. So interchange the ith and jth rows, then the determinant changes sign. Similarly, if you interchange the ith and jth column, then the determinant will change sign. If you multiply the ith row by k, or the ith column by k, then the matrix is multiplied, the determinant of the matrix is multiplied by that factor k. lastly, suppose that I pivot, do the pivot step. I add a multiple of some multiple, k, of the jth row to the ith row to get a new ith row. Or I multiply the jth column by k and add it to the ith column the ith column to get a new ith column. Then the matrix does not change. So in general, what that means is that how do I simplify finding determinants? Pivot. Pivot, and that will pivot where you make everything in the column that you're pivoting 0, or everything in the row, obviously besides the pivot, to be 0. Theorem. If A is a square matrix and 2 rows or columns are identical, then its determinant is 0. Page 610. Evaluate the determinant. So for problem number 8, I have this determinant. So it's a 2 by 2 matrix. So let's use that simplifying calculation for 2 by 2s. We'd say multiply -3 times -5, subtract 2 times -6. So I get 15 plus 12 is 27. So my answer is 27. In exercises 11 through 18, let A be the determinant of the 3 by 3 matrix. 1, 4, -7, -2, 5, 8, 3, -6, 9. Find each minor or cofactor. So let's find this minor. And so to find the minor, I do the following. I look at 2, I go over 2, so 1, 2, down 1. So this is a row, sorry. So I go 1, 2, and then go over 1. Well, so I remain here. So now what I want to do here is I want to get rid of this row and this column. And so this will just equal so get rid of that -2, 3. -8, 9. So I just got rid of, and maybe I'll do it in a really light color. Let's see. Here, wait. Let's move this out if I can. There, okay. I wanted this one. Okay, so I get, since I'm doing 2, 1, I want to get rid of this guy and this one. And so what remains is my minor. Okay, so it's only the determinant of -2, 3, 8, 9. Okay, so let's calculate that. So this is equal to -18 minus 24, which is equal to a -42. Let me do problem number 15. Oh, it's the same thing. Oh, but it's for the same one. Okay, good. Okay, so this cofactor is just equal to -1 to the 2 plus 1 times m sub 2, 1. So this is -1 cubed times negative 42, since we just calculated that. And so this is just equal to 42. And that's your answer. Now, another way of thinking about this is as follows. You always start here with a plus in the upper left corner. And as you traverse, you keep changing signs. So plus, minus, plus, minus, plus, minus, plus, minus, etc. And so in this case, plus, minus. And so since I was finding the cofactor using this guy, I go plus, minus. So I change the sign of negative 42 to get a positive 42. Evaluate each determinant by cofactors. So let's evaluate this. So first what I want to do is, whoa, okay, what in the world are you doing? Okay, it has a little bit of a mind of its own. What in the world? Okay. Okay, so sorry. My things are going a little bizarre on the computer. Okay, so let me get control back in my computer. I'm not moving, but things are moving. What in the world? Okay. Wait 1 second. Let me get control back of the computer. Okay. So let's do a cofactor expansion. So I notice here that I have 2 zeros. And so I'll try to make this easier. It really doesn't matter which one I do here. So let me pivot along this guy. And so this is equal to, I'm just basically going to take the third row, subtract from the first row to get a new third row. Everything else will be the same. So negative 1, 3, negative 2, 5, 2, 1, 0, 1. And so I'm going to subtract. So 1 plus 1 is 2. 3 minus 3 is 0. 2 minus 2 is 0. Negative 5 plus 5 is 0. Oh, that makes a lot of zeros. Okay, and then 2 minus 1, 0, negative 1. In this case, actually, I could expand along this one or this one because they all have lots of zeros. Let me do the expansion along this one. And so this will equal okay. So I'll just expand here. So I have a plus minus plus 2, but negative 2, times the determinant where I get rid of this guy and this. So I'm getting rid of this row and this column. So it's just 2, 2, 2, 1, 0, negative 1, 1, 0, negative 1. Okay. The rest of them are going to be a whole bunch of zeros. Because there'll be 0 times something else. So I'm not expansion. Now, let's expand along this. Because it has, this row here has a whole bunch of zeros. So this will make my life easier. So this is equal to negative 2 times plus minus. So it'll be a minus 2 times Well, let's get rid of this row and this column. So all that remains is 1, 1, minus 1, minus 1. Okay, so let's calculate that. And so this is equal to 4 times -1 minus a -1. 1 plus 1 is 0, so this is equal to 0. And so the determinant of that 0. So why would we want to do the cofactor expansion? Because doing the actual definition way of finding determinants is actually fairly difficult. So let me give the definition. I only gave you tricks. I didn't actually give you the definition of what it means to be a determinant. So let me give you that. A permutation. So a permutation of an ordered list S is a bijection from S onto S. Let me tell you about this symmetry group, S sub n. S sub n is a set of all permutations of 1, 2, 3, dot, 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 up to n, with composition as the group operation. Inversion. That pi, don't know why, inversions are almost always done with a symbol pi for some reason, don't know. Let pi be a permutation. Then the ij is an inversion if I is less than j and the permutation of I is greater than this permutation of j. So somehow if you change the order of these. Determinant. So the determinant of the matrix A with the ith, whose ith jth entry is A sub ij. Let it be a n by n matrix with real coefficients. Then the determinant of this matrix is defined as the sum over any permutation sigma of -1 to the inversion of sigma times the product from I equal 1 to n of A sub I in where the column would be the permutation of I, where this inverse the inversion sigma is the number of versions of the permutation sigma. Now, doing this definition on a computer for a 30 by 30, maybe, no, it says 40 by 40, matrix, basically takes the age of the universe. So when I said it was slow, it really is very slow. So what you would do instead is use these expansions, these cofactor expansions, which are much, much, much faster. Cramer's rule. Let A11 x1 plus dot 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 A1n xn equal B1 dot 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 A sub n1 x1 plus A sub n2 dot 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 A sub nn x sub n equaling bn. So let this be a system of linear equations. Let A be the determinant of the coefficient matrix. Let A sub xk equal well, it says here, the determinant of B sub ij, where Bij is A sub ij if j is not equal to k, and is equal to B sub I if j is equal to k. A sub x sub k is just the determinant of the matrix, coefficient matrix A, whose kth column is replaced by the non-homogeneous matrix. If the determinant of this coefficient matrix is not 0, then I can determine is equal to x sub k is just equal to a sub xk over a. And so this gives you a definite formula, so long as you have a consistent and independent system of linear equations, so long as you only have one solution. 2-point form for the equation of a line. Well, the 2-point form for the equation of a line is given by this determinant. So it's a nicer way of writing the 2-point form for the equation of a line is just by saying, well, it's just equal to this determinant. The determinant what is the determinant? Pipette, determined by the rows and columns of the matrix. How do you find the area of a triangle? Well, it's 1/2 base times height, but what if you don't know the base and height? Then you go, well, maybe you can use some trigonometry. You don't know trigonometry. Even at that, you still have to know like a base and an angle. What if you only know the location of the vertices of your triangle? Well, then you're sort of stuck. But this will give you the area of a triangle where you just know the vertices. So let x1, y1, x2, y2, x3, y3 be the vertices of a triangle. Then the area is 1/2 the determinant of x1, y1, 1, x2, y2, 1, x3, y3, 1. Unfortunately, you don't know if that's positive or negative. So at the end, and that's why I use the determinant, so that this really is an absolute value. It's not a determinant. On page 611, use Cramer's rule to find the solution of each system, if possible. So the fact that it wouldn't be possible is if you have either an infinite number of solutions or no solution. There's no way that a formula that just gives you an answer. So that occurs when the determinant of the coefficient matrix is 0. So before you use this technique, always check the determinant of the coefficient matrix. If it doesn't work, then you don't proceed any further because Cramer's rule is not applicable. Problem number 40. Oops, let's get another page here. So let's look at the determinant of the coefficient matrix. So let A equal the determinant of 1, 3, -5, 2. So this is going to equal 2 minus a -15. So A is equal to 17, which is not 0. So that means that I can proceed. I can use Cramer's rule. So it's not 0. So Cramer's rule is applicable. So it can actually try to solve this system using Cramer's rule. So let's do a sub x. And so the coefficient matrix is 1, 3, negative 5. Well, I'll just write down 1, 3, negative 5, 2. But what it's to find this other matrix, I replace the x column by the right-hand side of my equation, negative 6, negative 1. And now let's figure out what this is equal to. 12 minus 5 is negative 17. Let's do the same thing for a sub y. And so it is 1, 3. And then put in the non-homogeneous part. So a sub y is negative 1 plus 18. Insert page. Insert a new page. And so I get that a sub y is 17. Therefore, I get x is equal to a sub x over a, which is negative 17 over 17 negative 1 and a sub y over a, 17 over 17 is just 1. And so my solution is negative 1, 1. And so that's a solution to my system of linear equations. Use determinants to write an equation of the line in standard form that passes through the given points. So first, let's do the 2-point form. So I have 2, let's write xy 1, 2, 3, 1, 6, 8, 1. Okay, so let's do this. So I know that this is supposed to equal 0. And so let's do the determinant. So 1, 2, 3. Let's find my determinant. So 1, 2, 3. So that's 3x. The 1, 2, 3. 2, 3, 1. So 2, 3, 1. That's 6y. Why is this moving all over the place? Okay, so 2, 3, and now 3, 1, 2. 3, 1, 2 is 16. Okay, go in the other direction. 1, 3, 2, 1, 3, 2, minus 8x. 3, 2, 1, 3, 2, 1, 18. 2, 1, 3, minus 2y equals 0. Okay, so let's combine like terms. And so I get minus 5x plus 4y minus 2 equals 0. I want to write this in standard form, so I'm almost done. Now, let's add 2 to both sides of my equation. And so I get negative 5x plus 4y equals 2. Let's multiply everything by negative 1. So I get 5x minus 4y equals negative 2. Now it's in the preferred form for standard form, where there are no common factors. The coefficient in front of x is greater than 0. And they're all integers. 57. Use determinants to find the area of each triangle with vertices at the given points. So first, let's calculate this determinant: 2, 3, 1, 10, 8, 1, 0, 21. At first, so let's do 1, 2, 3. Oh, actually, I did that. So let's do 2, 10, 0, 3, 8, 20. So let's do it this way. So let's multiply. So I get 16 plus 0 plus 200 minus 0 minus 40 minus 30. And so that is 200 minus 70 is 130, plus 16 is 146. Oh, okay, good. So the area of the triangle is equal to 1/2 this determinant, I don't know what I'll call it, determinant of a prime or something, in absolute value. So the area is just equal to 1/2 times 146, which is equal to 73. So the area of my triangle is 73.